Hello, everyone, and welcome to the February 2026 Integration Down Under. Our organizers are Martin, Dan, Mick, Wagner, and myself in Melbourne. And tonight we have Elder from Microsoft to talk about engineering for reliability, stability, and Azure managed services. And I've known Elder for a while. Through the MVP program and then went to work for Microsoft. So let's get on without any delay. And here we go. Let me remove mine, add you to the stage. And there we go. And I will hand over to you now, Elder.
Perfect. Thanks so much. Yes, so first of all, welcome everyone for being here today. And of course, thank you, Bill, for having me here. So in this session, I will talk about engineering for reliability and stability in Azure Messaging, and then specifically for Azure Service Bus and Event Hubs. Let me start with a quick introduction. I'm Albert Grotenboer. I'm the product manager for Azure Service Bus. And in this role, I represent our customers internally and make sure that your voice is heard within our team. So I work closely with customers and the community. And one of the questions I regularly receive is, how do we architect a highly reliable solution with Service Bus or Event Hubs? So that's exactly what I want to talk about here today. I will share what I have learned from working with our customers so that you can design for high reliability and optimal stability in your own systems. And to set the right expectations, this session will be at an architectural level, focusing on the principles and the guiding questions that you can apply in your own environments. So anything that can go wrong will go wrong. Everyone has probably heard Murphy's Law before, and in our context, it basically means that you have to accept that failure will happen. Distributed systems are inherently suspect for failures because there are many moving parts, all of which can experience issues at some point. So when we talk about reliability, we talk about preparing for failure, not taking failure away. You need to prepare for where things go wrong. And when they do, you need to make sure that you can handle them without your entire solution breaking. So once you accept that failure is inevitable, you need a framework to understand where reliability actually lives in your messaging solution. When we think about reliability in messaging, there are basically three main pillars that you need to focus on. The first is the platform, which in our case means your Service Bus or Event Hubs namespaces. The second is your client application hosting environment, where you are running your client code. And then the third is the client code itself, what you're actually running. Now, each of these has its own levers, its own limits, its own failure protections. And it's important that you understand these thoroughly and implement reliability across all three of these pillars. So which availability options are you going to have, does the platform provide? What configuration work do you need to do? Are you going to run Kubernetes so you can run in any location? Or are you going to run functions and take advantage of the built-in support for Service Bus and Event Hubs through bindings? And which features are you going to implement in your code base? And what defense do you need to build around them? So all of this together basically builds your foundation. But thinking about reliability is not something that you do only once. It's something that you continually have to come back to. So that brings us to the life cycle of our solution, because reliability shows up at every stage. It starts with architecture, where you define the bounds and restrictions that your solution will operate in. So which service are you going to use? When will each service be used? What SKUs are they going to run on? How do you handle scaling? What parts of the platform can you leverage? And what do you need to build yourself? Then in the design phase, you will start filling in more details. Which message parameters are you implementing? And which features do you use, such as out-forwarding, sessions, or capture? Each of which themselves brings its own reliability requirements and impact. And which failures can you actually expect? And how do you make sure that you can actually recover those? Then you start moving into implementation, where you ensure that you actually have the proper error classification and retry logic. You implement back pressure and concurrency controls. And you ensure that you take advantage of the scalability of your messaging services without overloading them. You also think about idempotency and workflow compensation, so that the work is done exactly once. And of course, you have to implement proper logging, so that you can actually troubleshoot effectively when those issues do occur. And that brings us to our operations. This is where you will set up your monitoring to understand how your system is behaving. With Azure Service Bus and Event Hubs, you actually get Azure Monitor integration out of the box, providing you with a variety of metrics to understand the health and workings of your namespace. Make sure you understand these metrics, as they give you early insights into the issues that might come up. For example, if your letter queue starts building up, or your queue depth increases, this could indicate an issue with your consumers. Or if your replication lag goes up, it might indicate an issue with your Geo-Replication that you should investigate. And more on that later. Alerts are also essential here. You want to be alerted when something out of the ordinary happens, and not find out by chance, and certainly not find out after a failure already has occurred. And speaking of not leaving things to chance, you have to make sure that you run regular drills. This allows you to practice what you will do when an actual failure happens, because you have already gone through the procedures beforehand, and you do not have to figure everything out in the moment. With that foundation in place, let us take a step back and look at the Azure Messaging services themselves, because choosing the right service is one of the first reliability decisions that you're going to make. So most people that are watching this probably have already some familiarity with Azure Messaging services, but let us have a quick look at them before we continue. And here we are going to focus on Service Bus and Event Hub specifically, and how choosing the right services is one of the earliest and most important decisions that you will make, because actually each service is designed for very different scenarios. Now, Service Bus and Event Hubs are both built for very specific messaging styles: enterprise messaging and streaming events. To be specific, Service Bus is a PubSub broker that is used for pool-style queue-based transfer of jobs and control via message queues and topics. Event Hubs, on the other hand, is an event stream engine that is used for partitioned, high-volume, tape drive-style sequential recording and unlimited pool-style rereads of event streams. This distinction is important and is one of the earliest choices that will impact the stability of your system. While both services have overlap in functionality, they are specialized for different scenarios. Trying to force your solution into the wrong service will create issues in the long term. If you need a PubSub platform that provides enterprise messaging features such as sessions, transactions, dead lettering, duplicate detection, scheduled messages, and rich filtering on topics, or integrate directly with JMS ecosystems, Service Bus is the way to go. If you need to ingest high-volume streaming for data at scale, where you take advantage of partitioning and consumer groups for massive parallel processing, replay events from a retained log, or integrate directly with Kafka ecosystems, Event Hubs is specifically designed for that purpose. These specializations are important to understand before you make any other architectural decisions. And since we're talking about Service Bus and Event Hubs and about namespaces, one of these first architectural concepts you have to understand here is that namespace, because this is actually the resource that everything in Service Bus and Event Hubs is built upon. A namespace is the top-level artifact for both Service Bus and Event Hubs. It contains your underlying entities, such as queues, topics, and Event Hubs. And when you create a Service Bus or Event Hubs resource in Azure, the namespace is what is created and deployed first, before you define any of the underlying entities. So with that understanding in place, let's now have a look at how we can implement reliability from the platform perspective. And so as we discussed earlier, like in our earlier slides, we had those three main pillars. So those are the three main pillars when it comes to reliability for messaging solutions. And we are going to first look at the broker platform, which means the Azure Service Bus and Event Hub services, the namespaces, because this is where your most fundamental reliability and availability decisions begin. The foundation is actually defined by a few core choices that you make up front, and these choices will shape the reliability posture of your entire solution. So once you have chosen that service that you're going to use, like I said, enterprise messaging or streaming events, the next decision is the SKU that it will run on. So Service Bus offers the basic, standard, and premium SKUs. Event Hubs offer the same SKUs and also an additional dedicated SKU for full cluster isolation. The basic and standard SKUs run on shared multi-tenant infrastructure. Your data is always isolated, but underlying compute and memory are shared with other customers. Because of this, you can actually run into noisy neighbor situations, where other workloads consume all the available resources, and your operations experience temporary latency spikes. Now, these basic and standard SKUs also have some feature limitations. For example, Geo-Replication, that we'll come to in a moment, is not available on the basic and standard SKUs. Also, your throughput is capped. So, for example, on Service Bus, the basic and standard SKUs have a hard limit of 1,000 messages per second for ingress and egress combined. Now, the premium SKU provides dedicated and isolated resources for your namespace. So a specific amount of compute and memory is reserved there for you, which means that other customers can actually not affect your workloads. Premium uses messaging units for Service Bus and processing units for Event Hubs, which basically each represent a slice of those dedicated resources. So it's basically a slice of CPU and memory that we set aside for you. This SKU, the premium SKU, is also where features such as Geo-Replication become available, and where you gain much more control of your scaling posture. For example, on Service Bus, we allow you to scale from 1 to 16 message units per partition with up to 4 partitions, which means that you can have up to a maximum of 64 messaging units. So an important aspect of the SKU choice is actually future-proofing. With Event Hubs Premium and Dedicated, you're not just buying isolation. You are buying the ability to grow safely over time. You can scale independently, and you can plan partitions so that throughput and parallelism can evolve with your workload. Service Bus Premium offers a similar model, although with one caveat. Partitioning on Service Bus Premium currently is fixed at namespace creation. This is something that we want to change in the future, but right now you can only choose the number of partitions where you create your namespace. If you do create a namespace with a larger amount of partitions up front, you can then later scale your message units without needing a redesign or migration. And basically how that works is per partition you can have 1 to 60 message units. So let's say you choose 2 partitions. That means that you can scale from 2 to 32 message units. Now, as mentioned, Event Hubs also offers a dedicated cluster SKU, where you receive an entire cluster with no other customers sharing this infrastructure. So there's actually an entire Azure cluster, an entire Event Hubs cluster that's completely dedicated to you. This is an ideal choice for very large throughput scenarios or when full isolation is required, for example, due to regulatory constraints. Now, as you can see, your SKU choices define the baseline of your reliability and availability. It determines your isolation, your throughput capabilities, and the features that are available to you before you even begin to design the rest of your architecture. And once that baseline is set, the next layer of reliability comes from how the platform replicates your data. So let's talk about what we as the platform provide you when it comes to data replication. On every SKU in every region, your data is stored as 3 synchronous replicas. These replicas are placed in separate fault domains. So even if an entire rack fails inside the data center, the platform automatically fails over to a healthy replica without any user action. There's nothing that you have to configure for this, and it's completely built into both Service Bus and Event Hubs. And all data is written to all 3 replicas before the client receives an acknowledgement. So by the time the operation completes on the client side, the data is fully persisted across all 3 fault domains. This gives you rack-level resilience, and it forms the foundation for the higher availability options that we provide on top of this. Now, Azure also provides the concept of availability zones. These are available in specific regions. A full list can be found in our documentation. And if you run your service bus or event hubs namespaces in one of those regions, zone redundancy actually enabled automatically. This used to be different. It used to be something that you actually had to enable manually, where you would set a flag or something like that. But we changed that. It's now actually something that we automatically enable for you. And it's enabled in every namespace. There's no additional cost, and it works also now with all the SKUs. This used to be a premium only feature, but now it also works on basic and standard. So in this case, you still have 3 synchronous replicas, but in this case, they are distributed across 3 separate availability zones, where each zone is a physically independent data center, at least miles apart from the other. So with separate cooling, separate power, and separate networking. And just like in a single zone setup, if the primary replica fails, the platform automatically promotes a healthy replica in a different zone. Once again, this happens immediately. There's no user interaction and no customer impact. So zone redundancy gives you protection within a region. However, on top of that, we can also provide even more reliability options that span multiple regions. So just to very quickly recap what we had so far. Single zone, everything is in a single data center, but in different racks with fault domains. Availability zones, those 3 replicas actually spread across 3 different zones. And if you want, we can also enable Geo-Replication. So if you want even more control of your reliability posture, Geo-Replication is now actually generally available for both Service Bus and Event Hubs. With Geo-Replication, we replicate both your data and your metadata to a secondary region of your choosing. Each region maintains its own set of 3 synchronous replicas, in either a single zone or availability zone protection, depending on the regions you select. The regions are operated isolated from each other and often run on different deployment rings as well, which provides additional fault containment. Geo-Replication is available on the premium SKU for both services and also on the dedicated SKU for Event Hubs. So this is a customer-enabled feature, and you can turn it on per namespace. So the previous 2 features, like the single zone and availability zones, we turn on automatically for you. This is something that you turn on yourself, and where you will choose the different regions that you want to run in. So this feature introduced several architecture behaviors that are very different from what you might know from today from Azure Messaging, if you have been working with Azure Messaging before. Now, since Geo-Replication is still a relatively new capability, like I said, we just went GA for Service Bus. We went GA just before Christmas. Event Hubs, I think we went GA around November last year. So this is still relatively new, and I can imagine that there's enough of you that have not heard about this feature yet. So let's talk about a bit, what is this Geo-Replication feature exactly? The first thing I want to call out is that you should not confuse this with the older metadata GeoDR feature that many of you might be using today. So for those that have been using Service Bus already, you might know about this metadata GeoDR feature. That older feature only replicates a subset of the metadata. So it basically only replicates your queues, your topics, your event hubs. It replicates some of the configuration, but also not everything. But most importantly, it does not replicate your data. And it does not offer the broader architectural improvements that Geo-Replication does deliver. Now with Geo-Replication, so the new Geo-Replication feature, you are receiving full data replication, full metadata replication, and a significantly more robust reliability posture. If you are still using the older metadata GeoDR capability, I strongly do recommend that you pay close attention to this section, because you should start planning your migration to this new Geo-Replication feature. There are several architecture behaviors that are important to understand before you use it, which I will go to now. So first, let's walk through the core concept of how Geo-Replication works. So there's a single namespace with replicas running both a primary and a secondary region. This is already very different than the old GeoDR metadata replication, where you actually had 2 different namespaces that you had to link together, and where you actually had to manage them both, etc. Here you just have a single namespace. So you create a single namespace and you just specify this is my primary region, this is my secondary region. The secondary region operates as a hot standby, so you cannot access it, but it does have identical configuration and resource layout as the primary region, so that when you do failover, you can complete as quickly as possible. Which literally means we are just running the exact same namespace as you're running in your primary, you're also running in your secondary. We replicate the entire namespace, including all the metadata, such as the entities, RBAC configuration, network setting, as well as all the data. So all the data that goes through is also being replicated. We also replicate all the state transitions. So operations like complete and abandon, so that when you do promote to the secondary region, your message state remains in sync. And all of this is designed to give you a consistent and predictable geo-replication experience while keeping the configuration model straightforward. Now, these fundamentals do influence how replication behaves in practice, so let's have a look at that. So within geo-replication, there are two different replication modes, synchronous and asynchronous. So with synchronous replication, every request that comes into the client is first stored in the primary region. It is then replicated to the secondary region, where it's committed, and then acknowledged back to the primary. Now, once the primary receives that acknowledgement from the secondary, it then commits the change and then returns an acknowledgement back to the client. So once the client receives that acknowledgement, the data is already committed in both those regions. And like I said, both of these regions also have three instances of that message in both regions. So there's now 6 instances of your data. And of course, this all applies to data itself, as well as those state transitions as complete and abandoned. For synchronous replication, this does also mean that your application publishes at the end-to-end rate required to publish, replicate, acknowledge, commit across both regions, and that rate also depends on the availability of both regions. So if one of the regions is not available, your client cannot continue to send in anymore. Now, like I said, there's many upsides of this, of course, like RPO 0, like you don't never lose data, even if an entire region goes down. Downsides, of course, like reduced latency, and of course, if one of the regions goes down, the other region is also not available until you do something or that region comes back up again. Now, if you can actually handle some data loss, and we'll talk about the data loss in just a second, we also have the asynchronous replication. And with asynchronous replication, all requests are committed on the primary region, and then right away, acknowledgement is returned to the client immediately afterwards. So this is basically exactly the same behavior as you would see today without geo-replication, like you commit to the primary and you immediately get an acknowledgement. And then replication happens to the secondary region asynchronously. Now, you can configure the maximum acceptable replication lag for your asynchronous replication. And this is the offset between the latest action on the primary region and the latest commit on the secondary region, or the RPO, the recovery point objective. Now, if at any point the lag for the active secondary region exceeds that of the configured threshold, so that threshold that you configure, if it at any point exceeds that, the primary will start throttling incoming requests to ensure that that RPO, that recovery point objective, is not violated. So basically, once again, synchronous RPO 0, data has to always be stored in 2 locations before it gets acknowledged back to the client. Asynchronous is your RPO plus 0, where you specify the RPO, but with the advantage, like it's faster, like you don't have the whole round trip. And here, even if the secondary will go down, your primary will continue working. But of course, there's the trade-offs, as with everything, like also sounds like architecture. There's always trade-offs. So think about what is more important for you. Like, do you need RPO 0, or do you need like more application uptime, faster application, and choose the right mode here. So these replication mode choices also directly affect what happens when you initiate a promotion. So you as the customer are in control of promoting a secondary region, giving you full ownership and visibility during an outage resolution. When you choose a planned promotion, the service first places the primary region into an internal read-only mode. Now, at this moment, your clients will not be able to connect at this point, and they will receive a response indicating that the promotion is in progress. Now, this would also be a really good exception for you to catch in your client application and handle this with the backing of retry pattern until the promotion completes. Because at this point, you know, like, hey, it's going to come back. It's just not available right now. Now, if you are using asynchronous replication, the service will start catching up on any data that has not been replicated yet to the secondary region. And here comes that point where, like, you specify that RPO, how much data lag is maximum data lag you allow. So let's say you specified I allow 30 minutes of maximum data replication lag. So your RPO is 30 minutes. Now, of course, we try to keep up with that as much as we can, like we are constantly replicating. But let's say at some point we have a minute of replication lag, which is still well within those 30 minutes. But now you want to fail over or do promotion. You still want to actually have that 1 minute of data because you are basically just promoting because there's not a major outage or something going on. There might be an outage in a different system, or you might just be promoting because you want to run in a different region. So you still want to get that data over. Like, you know, hey, my primary is still working. I can still get the data over. And that's where you use that plan promotion. So at that point, we stopped incoming traffic. We are now replicating that 1 minute of data or whatever is there. And once that replication to the secondary has completely caught up, then the secondary is promoted to the primary. So the replication has caught up, and now we're going to promote the secondary to primary. So now we have the old secondary is now the new primary. And at this point, we also do the DNS endpoint switch over. So that the DNS endpoint is switched over to point to that new primary region. So as you can see, now this region is listening to your endpoint. That also means that your clients don't have to change anything. At this moment, as soon as the DNS endpoint has been switched over, your clients will just reconnect on that promoted region and continue their workloads. Meanwhile, the old primary has become the new secondary, and it now also begins its replication from the new primary. So basically now that picture is just reversed, it will now start replicating this way. Now, if replication cannot start right away, for example, there was an outage on that original primary, so this region is actually down, so it cannot replicate at this point, that region will remain in an in-build state. And it will start catching up, and once that replication lag drops below your configured recovery point objective, that new secondary then becomes fully active, and then replication will resume normally. So that does mean even if this, this region was down, you did a promotion, this will now start working, and then it will just wait for this one to catch up before it actually becomes active, and then it will continue as normal. Now, instead of a planned promotion, or actually any time during so instead of planned promotion or at any point during a planned promotion, you can also initiate a forced promotion. And with a forced promotion, we immediately promote the secondary region and switch the DNS without waiting for that catch-up. Now, of course, that does mean that any data that was not replicated from the old primary to the old secondary at that point will be lost. So be careful when you do a forced promotion because you might lose data. So one thing I'll call out here, of course, if you are running synchronous replication, this catch-up step is not needed because the data is always in sync. So that data catch-up is only actually used for asynchronous replication. Now, at this point, it should be clear that adding geo-redundancy to service bus or event hubs does not mean that your entire solution is geo-redundant. You just now made service bus and event hubs geo-redundant. Your solution, however, may also include other stateful components, databases, maybe some stateful apps, and so failover likely needs to occur at several different levels. Moreover, building a geo-redundant solution in Azure also requires you to bring in some Azure networking fundamentals. Some of these are straightforward. For example, if you want communication between your virtual networks, you need to ensure that you do not use overlapping IP address ranges. You also need to have some understanding about virtual network peering, so that application in one virtual network can reach the resource in the other virtual network during failover. Because of course your primary might be in one virtual network, your primary will be in one virtual network, your secondary will be in another virtual network, so make sure you have set that up. And finally, you also will need to understand how DNS operates when you combine this with networking level isolation. Now, this becomes critical when your clients need to resolve the correct endpoint during regional failover. So, of course, network design, once again, is only also one part of the application redundancy. Your hosting model also plays an equally important role. And so this is actually that second pillar that we were just talking about in the earlier slides. So now we are moving into how the application hosting model also influences reliability, independent of the capabilities of the messaging platform, actually. Because even the most reliable messaging platform cannot compensate for an unreliable client architecture. Where your application runs directly determines how it behaves during zonal disruptions, regional failovers, and DNS reorientational events. This also direct ties in what you own versus what the platform provides. Now, most people will probably seen some version of this diagram. But from a reliability standpoint, it is important to understand which responsibilities fall on you and which responsibilities are handled by the hosting provider. And this is critical because platform capabilities may vary. And you cannot just assume that the higher level services, so the further to the right you go, that automatically that gives you better reliability. So for example, Azure Functions, which is a fast service, so here that second column from the right, so it's a fast service, but it does not provide Geo-Replication out of the box. So if you are using functions, you do have to build something on top of that yourself. On the other hand, you could go for something like containers as a service, CAS, with something like Kubernetes, which you can also configure to be highly available. But doing that on something like Kubernetes also requires to have deep expertise because it's far from straightforward. So, like, depending on which pillar you're in, you might have different options, but you also still need to make sure that you know what is actually provided for you. And then, of course, also know how can I build this myself. Now, if your application allows for it, you could host them, for example, Azure App Service, although that might also induce its own constraints. We do sometimes see customers running the client application in AKS, so they can then move their workloads to another cloud in case of an outage. However, that does not help much when the rest of your solutions, such as your databases or your message brokers, are still in Azure and you did not set up redundancy for them. So your hosting choices matter. However, there's no single correct answer here. The right approach depends entirely on your requirements and the characteristics of your client applications. And of course, this becomes even more complex if your clients do not live entirely in the cloud. If they run on premises, at the edge, or even in environments with intermittent connectivity, that induce even an additional set of reliability concerns. Because you now have to start thinking about disconnected operations, delayed retries, burst to reconnect behavior, much longer failure windows. And all of this also refactors into your reliability design. So this is really something like you have to think about, like where are my applications hosted, my client application living, and where do I host these? And these specifics for your application must be kept in your architecture, because this is where you define the guardrails and guidelines which in your entire solution, including your client applications, must operate. So reliability and stability need to be core tenets of that architecture. That means your requirements must be explicit and measurable. How much downtime can your solution tolerate? And what is your recovery time objective? Are there options for replay? Or can you handle some level of data loss, defining your recovery point objective? Can your backend systems handle duplicate processing? And which workloads are actually critical to the business continuity? And once all these requirements are clear, you then need to ensure that the components that you select in your architecture support that. And the alignment between those requirements and component capabilities is what ultimately determines the reliability of your solution. So when you do choose that hosting model, you do need to evaluate it through the lens of those reliability requirements. How reliable has that hosting model been before? How many levers does it provide to ensure the stability? What high availability options are available, both built-in and those you can add yourself? Are there proven technologies or proven patterns that can further improve reliability? And if something does go wrong, how long will it actually take for that environment to come back online? All of these factors must be considered carefully because your hosting model has a direct impact on how resilient your application is going to be. So now we are moving into the third pillar, the code itself. And so this is your client application code. Because even if your platform, so your messaging platform, your application hosting platform, even if they have been completely configured for full reliability, if you have an unreliable implementation or if you have failures in how you follow best practices, that will still undermine that foundation. When you work with Azure Messaging services, there's actually several features and levers that you can use directly from your code to improve the resilience though. These allow your clients to handle transient and persistent issues, and they can also help you recover cleanly from impactful events. So as you implement your client applications, there are several reliability aspects that you need to account for. You may have multiple producer and consumer applications with different responsibilities, but they all need to be reliable, stable, and be able to handle issues when they occur. Now, the Azure Messaging SDKs actually includes several built-in mechanisms that you can use with minimal effort. So for transient issues, for example, such as connection drops or timeouts, the SDK automatically performs retries, and that uses retry logic that you can actually configure yourself with that. So this minimizes the impact of transient failures because client already just simply retries the operation, so you don't even see a failure happening, like you don't even get an exception. And even if an entire connection or link is dropped, the SDK does detect this and then applies that same retry mechanism. Throttling is another scenario that we often get questions about. And as we discussed earlier, on the service bus standard tier, for example, you will get throttled when you exceed 1,000 messages per second. However, throttling can also be caused by other factors, such as noisy neighbors or a high service load. Now, most of these throttling events are transient, and the SDK actually handles them automatically. So make sure that you have a look at how to set this up and use those capabilities. Now, of course, there's also non-transient issues. Like, for example, if your schema doesn't validate, like if your message is malformed, that's not going to solve itself by just retrying. But for those non-transient issues, there's also additional mechanisms that can prevent data loss. In Service Bus, we support dead lettering, so you can isolate messages that cannot be processed without blocking the queue. And Event Hubs actually continue checkpoints the progress. So even in the event of critical failure, your client just resumes from the most recent checkpoints. Now, let us look at what you must implement yourself within your client codes. So you do need to understand what actual exceptions can occur and how you need to handle them. Some operations will succeed if you just retry them, while others require manual intervention. Like I just said, for example, that schema validation is something that will most probably need a manual intervention. The message is not just going to change itself, so you will probably actually need someone that's going to have a look at the message, maybe update the message, maybe even go talk to the people that are operating the source system and make some changes there. So when manual intervention is needed, you should move messages to, for example, a dead letter queue. And then also have a process that can act on those messages. And I really want to highlight this one because we do sometimes get customers that come to us like, hey, we have 1 million messages now in dead letter queue. How can we clean these? If you have 1 million messages in that letter queue, you probably did not have the right processes in place because there's 1 million messages that you did not process. Those 1 million messages were probably important at some point. So do make sure if you dead letter messages or if you set them aside in a different way that you do process them and can actually also process the message at some point. You also need to distinguish between functional issues, such as malformed messages, and technical issues, such as a backend dependency that's being unavailable. These also require different resolutions, and they must be routed to the right teams or systems. Like I said, a malformed message might need someone to repair the message or to go talk to someone that is sending those messages. A backend dependency might need to talk to the operations team or talk to the database team or whatever. Now, once again, here you also have different resolutions, so they need to be routed to the right teams or systems. So you can forward those messages, for example, from your lettered messages to a different topic. So this is service bus specific, for example, but you could move them into the letter queue and then use auto forwarding to actually route them to a topic. And then on the topic have different subscriptions, and then have different subscriptions, different issue types. And then behind those subscriptions have different places where they then go. For example, you might have a logic app that picks up messages that need to go to the operations team. You might have a function that sends messages into the mailbox of someone that needs to look into malformed messages. All different kinds of patterns here, all different kinds of ways you can handle this. But most importantly, do think about that. What happens if something goes wrong? Would we need to take a look at this? It's also important to distinguish between transient issues and actual failures. A single server error might be acceptable to retry. Might just be connection broke for some reason. However, repeated server errors might indicate a deeper problem that needs investigation. So track this behavior and make sure that you have a way to notify your operations team when you detect abnormal patterns. Consider how you want to handle log loss, like message log loss, or when you are receiving duplicate messages. So, for example, one that I especially on Service Bus side hear quite often, because of course Service Bus is really more about single-time processing, is if your connection resets and you lose the message log, you might already have processed this message, but now you can no longer complete it because your message log is lost. However, you can also not assume that no other consumer has processed it. Like another consumer might just have picked up the message and started processing it. So your application should be idempotent, either by design from the application itself, or maybe to some other logic that prevents duplicate work. Like maybe you have it in your client, maybe you have some in-between layer. But so make sure that you have that idempotency as well. More on that in just a moment. You need to think about batching as well. If one message in a batch fails, does that mean the entire batch should fail? Or are these just independent messages that simply were sent together? Downstream processing is another consideration. If your backend is throttling, you probably want to apply some back pressure because you don't want to overwhelm your backend system. And finally, you need to make sure that your operational signals leave your process. If everything is just logged into your console, your operations team doesn't have any visibility. So you need to emit the right metrics, the right logs, the right traces to systems such as log analytics and application insights, so that your teams actually can understand what's happening both during normal execution, but especially during failures. Now, luckily, you do not need to reinvent the wheel. There's a lot of meshing patterns out there that can significantly increase the reliability of your solution. So I'm just going to name a couple here. There's many more, of course. We actually have quite a few of them in our architecture center, in our documentation on Learn. But idempotency is the first one, because duplicates should be considered normal in distributed systems. Whether they come from geographic failover, a lost message log in Service Bus, a checkpoint being reset in event hubs. Basically, whenever you talk about distributed systems, be prepared for duplicates. And if duplicates do cause issues for your workloads, make sure you address those. If your downstream systems are not idempotent, you can implement idempotency directly in your client applications. For example, by storing a lightweight reference, such as the message ID. The other outbox pattern is another pattern that can help maintain consistency across partial failures. It actually allows you to track both the processing of your data and the data itself. And it gives you a way to detect when something was not fully processed. So this builds a more robust workflow, and especially in systems where multiple operations must succeed together. And the circuit breaker pattern is essential for preventing cascading failures. because when a system is experiencing major issues, the circuit breaker actually allows you to pause calls before they generate a large number of failures or retries or down system overload. And since you are using service bus and event hubs, they will just stay in those queues or those event hubs. And then your client can just come by later and pick them up. So this protects both your clients and the service they are dependent on. So these patterns are well established, and you do not reinvent your own resilient mechanisms. Applying these proven patterns consistently is actually what separates resilient systems from fragile ones. However, without testing, you're effectively blind to the issues you may have induced in your applications. Testing is how you verify the functionality behaves as intended, and that no regressions are created. For example, by using unit tests. You also need to validate all components work together as part of the full solution by performing integration tests, performance tests, stress testing, and making sure that you're not just using isolated component tests. And all of this, of course, must be automated so that your test can run every time that your code is built, it's checked in, is deployed, or at any other quality case that you define. Testing is not optional. It's really the foundation of reliability. It ensures that your code behaves correctly, remains stable over time, and does not regress as your solution evolves. Now, how do you ensure that once your solution is up and running, it also actually stays up and running? So after deployment, it's operations that determines whether your system remains reliable. This includes monitoring, alerting, observability, and proactive health management. You need to understand how your environment is actually behaving. The most important tools for this are your metrics and your logs. Metrics show how the platform and your applications are performing. From queue depth, incoming and outgoing metrics, you can actually see where the messages are being processed, and also whether your clients are keeping up with the workloads. The latter metrics tell you when messages cannot be processed. Other metrics might indicate when you are approaching limits, such as CPU or memory usage, or entity size, or throughput, and might actually tell you like, hey, I should be scaling up, or I might even be in the wrong SKU. Server and client errors signal that something is failing and that you need to investigate further in your logs. And of course, you don't want to be watching dashboards all day, so you also want to be notified when something abnormal occurs. Now, luckily, with Azure Monitor, Log Analytics, and Application Insights, we give you the tools to set up alerts and understand what is happening inside your system and react to that proactively. Also, in addition to monitor your own metrics and logs, customers should also be paying close attention to Azure Service Health. So Service Health is actually your primary source of truth for platform-level incidents, as well as planned maintenance and service advisories that affect your specific subscription and regions. We still see customers relying on the public Azure status page, but that view is actually intentionally high level. So that actually goes over all of Azure. Service Health, however, gives you targeted, actionable notifications that are meant to drive operational response on your specific resources. So you need continuous visibility in your system behavior. So metrics, logs, and alerts allow you to detect issues early, validate performance, and understand whether your applications can keep up with the demand. However, just knowing that something is going wrong is only the beginning. You also need to take action. And wherever possible, these actions should be automated. So once again, Azure Monitor provides automation capabilities, such as runbooks, that can actually help you do exactly that. For example, if parts of your solution are not working properly, you may need to pause processing, resolve the issue, and then restart the workflow. This is basically that circuit breaker pattern that we just talked about. Now, if an entire region is down, a failover needs to be initiated in another region. And like all of these can be automated through Azure Monitor with the help of runbooks. Also, if you are hitting scaling limits, you should autoscale, which basically means increasing the number of message units for Service Bus or increasing the number of processing units for event hubs. Once again, this is just a setting on your namespace. use it. It's there. It's very easy. It automatically scales up and down. And it's very important to make sure that you have enough resources so that you don't run into limited resources and at some point actually things are breaking. However, it's also important that you assume that scale-up can fail. Capacity might not be available when you need it. So your systems also need to be able to handle back pressure, throttling, and delayed recovery, rather than just assuming that scaling will always succeed. And of course, you also need to make sure that you start scaling on time and don't wait for the last second. Beyond this, there also need to be procedures for handling any fallout. So what happens if you did have issues going on and messages were dead lettered? Or do you need to reprocess event ops data from an early checkpoint where maybe during that failure time frame, some messages were not processed correctly for event ops? Can you then just reprocess them? Has all the data been processed as expected? Or do you need maybe even go and retrigger work from your source systems? Make sure you understand all of this beforehand so that you do not have to figure it out in the middle of a failure. And of course, no matter what, you should run regular drills. Because how do you know that your Geo-Replication promotion actually works if you never tried it? If you discover during disaster that you actually forgot to configure a virtual network for the secondary region, or that you did not set it up correctly, all that other preparation that you did is for nothing because now you still have downtime. So identify anything that you think of that can go wrong and make sure that you practice those things regularly. Because if you expect and prepare for failure, you will not get caught surprised when it actually does happen. Now, everything I've talked about here applies to your solutions, but we use the same principles also with how we run Azure Messaging at massive scale. So how do we do at Azure Messaging? So how does Azure Messaging actually perform when it comes to reliability and stability? Let's have a look. Every day, we do just under 15 trillion messaging requests per day. That's a lot of messages, by the way. We handle petabytes of data movement, and we support tens of thousands of paying customers, including all of the top 500 Azure customers. And we do this every week while delivering a success rate of 5 nines across all the messaging operations. Because we know that you rely on us for your messaging workloads, so we operate one of the most reliable, most battle-tested, high scalable messaging platforms on the planet. Our goal is to ensure that you can focus on building your solution without having to worry about reliability or stability of the infrastructure underneath it. And you can actually focus on all those other parts I was talking about. So with that, I would like to say thank you. I hope everyone enjoyed this session. Thank you for having me here, of course. And are there any questions?
There hasn't been any questions posted, but again, we can check and people can put a comment on the Facebook, and then I can get those to you if there's questions down the line.
Perfect.
So thank you very much. It was really good. I hadn't been through a lot of the pieces about the geo redundancy and things like that. So that was good to see that and the different options that you have. So yeah, that was very good. Thank you very much.
Thank you.
So again, any questions from Dan or Mick?
Eldred, I just wanted to echo Bill's sentiment too. It's always good to hear straight from the horse's mouth, and obviously we really appreciate having someone like yourself come on, and I mean 15 trillion messages a day is absolutely phenomenal, and then the level of monitoring and proactive work that's being done on it is really good, and I think what I took away from that was there's a part of your Microsoft, you should be doing that. What can I do in my solutions? However, what you're talking about there was something that we all can go and do from day dot on all of our solutions without too much effort.
Yes. Yeah. And like I said, this is all like from actual customer conversations. Like this is like, because I talk to a lot of customers, so I talk to a lot of community. So this is all from conversations with customers that ran into some issue where it's like, oh, this is what went wrong. Or just like architecture sessions and stuff like that. And I really think it's important that everyone knows these kind of things, because a lot of this might be things by people where they think about, oh, we thought about these 5 things, but the 6th thing we forgot, and that 6th thing, of course, broke, and now we have an outage. So that's why I think it's important, like having all these things in a row and making sure that people know about them and understand, like, okay, why do I need to think about this? And making sure that people just realize, like, yes, I should be thinking about this, or making a conscious decision, like, hey, this is something that we can ignore because, like, this doesn't apply to us, or this is a risk that we know that we take, but we can handle this in a different way. So, but at least want people to think about it. So that's why I think also that first architecture phase and design phase is so important, where think about what you're doing and set those right boundaries, right limitations, etc.
Yeah, I've run into people that they think about the redundancy and stuff after it's too late, once they've already built everything, and then they try to go back and retrofit that stuff in there, and it's a lot harder to do after the fact than it is before.
Yes. And I also think too, Elder, that when we talk about messaging and service bus and so on and so forth, it can be primary, the primary sort of aspect to it, where we've explicitly integrated into our solutions, or it serves some greater purpose. But then you look at a lot of the day-to-day technologies that you may use, such as data gateways and things like that. And what underpins that is exactly messaging. So it builds on already something that's quite phenomenally stable. And behind your data gateways, there's relays and service bus and a whole bunch of things that run, that support the execution of that. So even though on the surface you might say, hey, I don't have any of that, I don't think, in my solution, you could do everywhere.
Yep, indeed. Yeah, there's a lot of places where we run behind the scenes that you will never know about.
Well, guys, I do have a hard finish time today, but thank you very much, and definitely enjoyed it. So anytime you want to present on any other topics, just please let us know and we will get you scheduled in. So perfect. Thanks, everyone. And
that's good.
That'll be all for today.
Awesome. Thank you, everyone, and enjoy your day.
Yes. Thanks, crew.